There's two problems. The first one, and the two are depicted here. The first one is to give a data value in the list, one of the data values, and ask the question, well, what is the percentile? And so what the answer to that question is how far away, or how far from the start of the list to the end of the list does the data, what percentage of the way through the list does the data value fall? So the first thing that we have to do in any of these is to sort the data, because if the data are not sorted, then it doesn't make any sense to talk about a data value's position, because you can scramble the data values and it can be in several positions. But we want the unique position of the data value after the data set has been sorted. So remember to sort the data. And the second thing, all right, so this one here is to determine a percentile. Sort the data and then find the position of your data value. All right, so the goal here is to consider what we would call bivariate data, and the bi meaning 2. So we're going to have the x values go in x, the x values go in L1 and the y values go in L2. And we're going to describe the data set. So I'll give you some language today that'll help you do that. And the goal is, can we see a linear relationship between the two variables, the two numerical variables? That's basically what we're looking for. And since this is descriptive statistics, we're going to describe the relationship between those two variables, x and y. And there are 3 different things that we're going to use to describe the relationship. And the first one is a graph. And the graph we're going to use is a scatter plot. You know, some people write this as one word, scatter plot. Some write it as 2 words. Some call it a scatter diagram. But this is what it's going to look like. You're just going to plot a bunch of x and y points like this. And the trend you're looking for, or the relationship that you're looking for, is a linear relationship. You know, is it such that the x and the y values increase together as x increases, y increases? Or is the relationship an inverse one, where as x increases, y decreases? But more importantly, is that observed relationship, does it kind of conform to a straight line trend, or is there no trend whatsoever? So the first thing we're going to do to determine if there's a trend is to draw the scatter plot. And then the second thing we're going to do is we're going to calculate a statistic. And the statistic is the correlation coefficient. The sample statistic, we're going to be using the lowercase r. R is the sample correlation coefficient, and when we're looking at bivariate data like this, we're always going to calculate it. And I'll explain to you how you interpret that statistic. One of the things it uses are z-scores, and we talked about z-scores last time. And then a mathematical model. And the mathematical model may also be something that you've calculated in the past. It's the line of best fit. So we're going to plot the scatter plot, but then we're also going to draw a line of best fit so that we can see that the line matches the trend in the data. And then once we have an equation of a line of best fit, then we can use it to make predictions. All right, you may recognize it like this. Y equals mx plus b, that's the equation of the line. But the calculator is going to give us y equals ax plus b instead of mx plus b. But the number in front of the x is the slope, and the number that stands alone is the y-intercept. So this is why algebra is a prerequisite for this class, this course. The calculator will calculate those 2 coefficients for us, and the way that it's going to look is it's going to give an output of y equals ax plus b like that. It's just going to write that equation, and then it's going to give us the values. And then then you would take those numbers and insert them into the equation to get the equation of the best fit line. So that's it. That's where we're going. Those three things. The scatter plot, I can show you how to calculate or how to construct one of those on your calculator. But probably the correlation coefficient is something that maybe you haven't had any experience with, but maybe you have. So that's where we're headed. And so the first example is bone mineral density. So there's a medical procedure that you can figure out the strength in the bones. And I'm not sure if it's a biopsy of some sort or if it's a pressure gauge, but the y-axis variable is the bone mineral density. So you can think of it as the strength of the bones. And it's measured in grams per square centimeter. So we can just call this bone strength. And the x-axis variable is the number of colas. Yeah, that's right, like Coke and Pepsi, colas that you consume, that one consumes. And so they ask individuals who participated, how many colas do you drink in a week? And the respondents gave them the answer, 7, 1 per day, 0, I don't drink Coke, those sorts of things. And then they took that medical procedure to measure the strength of the bones. Now the researchers here probably felt that Coke is not a very good thing to put in your body, and that if you do put Coke in your body, then your bones will get weaker. And so if there's a relationship, then maybe it's, Coke causes, you got to be careful about saying causes, but there's a relationship between bone strength and colas consumed. All right, so generally what we're going to do is we're going to put in the x-axis variables and values into L1, and we're going to put the y-axis values into list 2. So let's go through and I'll show you the calculations on the calculator. Can you see those? You do have the, all right, go ahead and enter those values into your calculator because I want you to go through the steps as well. By the way, I did also include, I'm going to show you how to do this today, but there's a handout that says data analysis on the TI 8384, and this takes you through all of the steps of entering the data into your calculator, drawing the scatter plot, calculating the correlation coefficient, and the coefficients of the line of best fit. They kind of all are presented at the same time. So this is available at the e-learning site if you need to refer to it later. Okay, is everybody ready? Got them all in there? L1. You can also see that these bone mineral density numbers, they don't vary a whole lot. Just about for every participant in the study, the bone mineral density range from about 0.89 to 0.86. So there's not a lot of variation in bone strength for humans, whether or not they consume colas or not. So it's hard to just look at this data set and observe a trend. It's important that 0 matches up with 0.893, these go together, and then 0 matches up with 0.882 and so on as you go through. When you're done, you're going to have, what is it? 15 ordered pairs. The last one is 8 and 0.865. All right, let's go ahead and calculate some statistics from here. The first thing we're going to do, though, is to construct the scatter plot. So to do that, we need to set up this plot right here, stat plot. Same place where we drew the histograms, same place where we drew the box plots. When you're going to draw a statistical plot on this calculator, you want to set up the graph here. So second in stat plot, we're just going to go into plot number 1, turn it on, so make sure the word on is highlighted. And the very first graphic here is the scatter plot. That's the one you want to select. Now, when I hit enter here, and I'm going to hit enter in just a second, you'll see that for a box plot, you need only data in X list 1, frequency of 1. But for a scatter plot, you need the X list and you need the Y list. So as soon as I hit enter here, the calculator understands that I need 2 different lists to construct the scatter plot. So have it on, select this graph icon, L1 and L2, and then there's 3 different marks, and the mark is just how you want the calculator to plot the point. And I always use the big rectangle here so the points look bigger, but you can select whatever one you want. And the only time you're going to use the other marks is if you're comparing 2 different or 3 different scatter plots. And most of the time we're not going to be doing that. Now, it's always going to be the case that we need to set the window so that we can see all the points. If I just hit graph here, we're not going to see anything. So I want to make sure that my x's range from 0 to 8, and my y's range from about 0.8 up to 0.9, so that I see all the data values. But it's somewhat tedious to actually go to the window and change all those numbers. If I did, I would have to set my x-min at 0, or maybe I even set it at -1, and then the max I might go up to 9, scale of 1. And then for these values, I would need to go from 0.86 up to about 0.9, and then graph. And you can see it there. But that's an added step that normally we just don't want to bother with. It's much easier just to hit zoom and then go down to option 9, stat, and just hit zoom 9. Zoom 9 is the fast way to just have the scatter plot or have the graph calculator automatically set the x min, x max, y min, y max, so you don't have to do it yourself. And notice if I go back to the window that you can see the numbers that the calculator came up with are a little bit different than the ones that I typed in. So turn on the graph and then hit zoom 9 immediately without bothering to change the window dimensions. Ask the calculator to do it. All right, and you should see that the scatter plot that the calculator drew is very similar to the scatter plot that appears here. So this axis down here, number of weekly colas, and this one up here is the bone mineral density, strength in the bones. But you can clearly see a downward trend, all right? And if I just draw 2 lines that capture all of these points, it would look like this. So what you observe here is a downward trend. And this suggests an inverse relationship. And what we mean by that is as x increases, the y decreases. If they do the opposite thing, the x and the y, one increases, the other one decreases, then we say it's an inverse relationship. If we have a data set where as x increases, y increases as well, then we call that a direct relationship. So what this graph is suggesting is that people who drink more colas tend to have weaker bones. Now, we're not saying, be careful, we're not saying that colas cause weak bones. What we're saying is that there's a relationship, and there probably is not a causal relationship. There might be other variables out there that lead to weaker bone strength. Okay, so that is the first part of what we're going to be doing here, and that is to sketch the scatter plot. Look at the plot. There's a direct relationship. This is an inverse relationship, downward trend. So say something about the graph. Say something about the relationship. All right, so the next thing that we need to talk about is a statistic. Like when, just like the mean, when you get the mean, you have a sense of now what the data set looks like. If you know, for example, the mean is 15 or the median is 16, you know about where the center of the data are. The statistic that we're going to calculate in this setting is a correlation coefficient. And what, at the end of today, if you know what the correlation coefficient is, you should know kind of what the scatter plot looks like. That's what we're headed for. So let me talk about the correlation coefficient. By the way, we don't talk much about the population correlation coefficient, but it's this guy, and we pronounce it rho. It looks like a script P. It's the Greek letter rho. We use Greek letters for population parameters. In this case, the population correlation coefficient. And we may also look at that a little bit later on in the course. All right, the first thing that you need to know about R is that it will always take on a value between -1 and 1. And I'm going to show you some scatter plots that correspond to several of those values between -1 and 1. So here's a continuum. On the one side, we have R equals -1, and the maximum value of R on the other side is +1. -1, +1, of course, right in the middle is 0. All right, the scatter plot for if R is equal to -1, that's the minimum most value. So what you're going to see here in a scatter plot, if the correlation coefficient is -1, you're going to see a perfect linear relationship. All of these points will fall perfectly on the same straight line. But you'll also see a downward trend. So when the correlation coefficient is negative, think about it as, you know, the slope being negative. And if the slope is negative, then you're going to have a downward trend. Similarly, if the correlation coefficient is positive, then there's going to be an upward trend. And if the correlation coefficient is 1, the maximum value, then you're going to see a perfect linear relationship. It looks like this. All right, the one in the middle is 0. A correlation coefficient of 0, what that means is that there's absolutely no relationship whatsoever among the points. There's no observable linear trend in the scatter plot. And so these points are going to be all over the place. And there's not going to be a trend one way or the other. No trend, no linear trend. No upward trend, no downward trend. Okay, so as you move from absolutely no trend to the perfect linear relationship over here, all of these numbers are positive. All numbers between 0 and 1 are positive. And so if you have a correlation coefficient of about 0.8, so it's a positive number, and it's closer to 1 than it is to 0, then what you're going to see is you have a pretty strong direct relationship here, but several of the points will fall off the line. And so you'll get this kind of a wider trend path going up. You might even have a couple of points that fall off that trend. So generally the trend is like this, but maybe a point or two might not be inside that. But you have these triangular regions down here where you have few or no points. If you see those triangular regions with few or no points, if it's a skinny trend channel, then you're going to have a very correlation coefficient very close to 1. The wider that trend channel gets, the further away from 1 you get. All right, let's go over to the other side. If you had one here of, say, R is equal to -0.6, well, there's even more dispersion in the points further away from a linear trend than with the 0.8 case. So in this one, you're going to see the data values go down like this to represent a downward trend. But then because these points are, you have a much less than 1 in your trend, you might see a wider trend channel here, and you might see more than just 1 point in that upper and lower triangular region. So if you compare these two, the 0.8 has a skinnier trend channel than the -0.6, and the trend also over here on the positive is an upward trend, and over here it's a downward trend. So over here, you're going to have an inverse relationship, and over here, you're going to have a direct relationship between the two variables x and y. Now, when you have like a correlation coefficient of, say, 0.2, it's going to be difficult for you to discern the difference between a correlation coefficient of 0.2 and a correlation coefficient of, you know, say 0. Because with this one, you know, we do know that we have a positive trend, but because the correlation coefficient is a positive number, there's going to be an upward trend here. And so, you know, maybe here's this big, thick trend channel, and, you know, most of the points are clumped together in that wide channel, but there are still a couple of points in the upper and lower triangular regions. So it's really hard to discern this. My goal for you is to be able to know that this one's positive 1, this one's negative 1, 0 looks like there's no trend at all, and then, you know, to be able to identify a positive trend, which corresponds to a positive R value or a direct relationship. And then if you see a negative R, then that means you have a downward trend. The closer the correlation is to 0, the more it's going to look like there's absolutely no trend. Okay, now what I'd like you to do is to take a minute to write what you think is the correlation coefficient of each of these 8 graphs on the top. All right, I'll label them A, B, C, D, E. And I'll ask you to put your estimates of the correlation coefficient in the chat box. So let's start off with part A. What do you think the correlation coefficient is? Now, I'm asking you to estimate what is the value of R. Now, there are some correct answers, there are some incorrect answers, but some of these, there's just one correct answer, but most of the other ones, it's kind of hard to tell what that correlation coefficient is. Okay, so what's the correlation coefficient of part A? Go ahead and put your answer in the chat. Yeah, so yeah, you're right. It's a perfect upward sloping scatter plot. Correlation coefficient is 1. What about D? Let's do D next. What's the correlation coefficient, do you suppose, on D? Okay, so this one has a downward slope. So the slope of a line that would go through those points would have a negative slope, and it's a perfect linear relationship. So yes, this one is -1. What about E? Here you got a couple of gaps between the points, where here they all appear uniformly the same. What's the correlation coefficient, do you think? What would you estimate it to be for part E? Okay. Also -1. It doesn't matter if there's gaps between the points, as long as all those points would fall on the same straight line, then correlation coefficient is 1. Okay, what about F? Put your answer in the chat. Now, all the answers are going to be different, right? I mean, you have an infinite number of possible values there. But what the features you look for are, is the trend going upward or is it going downward? And are the points kind of all clumped together in that trend channel, or are they kind of more widely spread out away from that trend channel? All right, so when you see a lot of good answers there, all negatives, that's good because it is a downward trend, so negative. But when there's so few points in the lower and upper triangular regions, this is going to be even higher than the 0.8. So it's probably going to be something like, you know, a -0.95 even. And as you're calculating more of these, and you look at more data sets, you'll be able to get a sense of, a better sense. Okay, let's do B and C together. Write down the correlation coefficient. And what I want you to do here is estimate the correlation over here in part B, and then use whatever you had there for B to write another estimate for C. So give me B and C together. Okay, so I'm more interested in the relationship between those two than what specific value that you have. This one here, you know, it's a little wider trend channel than say this one down here, if the scales are the same, but it's going to be positive. So, you know, this is probably 0.9. No points down here, no points up there. So the trend channel can even be a little wider, but no points down under the trend, and no points up here. So that's going to make this very, very close to 1. And if you chose a number here, then this one is going to be a little bit less than that. There's still no points down here and no points up here. So, and the trend is upward. So it's still going to be a positive number, but maybe this one is 0.8. And it's 0.8 because there's no points in this upper triangular region, and there's no points in that lower triangular region down here. Even though the trend channel is a little wider, so then the correlation will be a little bit less than the 0.9, but it's still pretty strong, pretty close to 1. And then finally, let's do G together, and then use your answers here to kind of help you answer these. So give me G and H. And again, I'm more interested here that you're the comparison between the two correlation coefficients that you write down, rather than, you know, whether you get 0.6 when it should have been 0.7 or something like that. So what's key is that you get it right in terms of whether the correlation coefficient is positive or negative. And the other thing is the relationship. Which data set is more spread out away from the trend line? The data set that's more spread out will have a smaller correlation. Okay, I think those are the answers. 8.5. Okay, so, you know, if this is the trend channel here and we make a similar trend channel here, you know, this point here is away from the trend channel a little bit more. By the way, when you're looking for outliers, you're looking for points that don't focus on their X value or their Y value, but focus on how far away they are from the trend. So the only candidate for an outlier here would be this one here, a point that sits outside the trend. In some of your problems, it'll say, you know, if there is an outlier, which data value would it be? And for this one, there's only one candidate. It would be this one here. Okay, so even these graphs, we have very few points in the upper and lower triangular region. So this one's probably going to be about, you know, 0.85, and then this one is just a little bit less than that, maybe 0.8, because that one data value falls away from the trend. And I think because of that one data value, you should have a lower second number than a first number. All right, one last one. What would you guess the correlation coefficient to our bone mineral density in colas example to be? Let me point you to the downward trend, point you to the fact that there's no points underneath the trend line, the trend channel I should call it, because it's not a line yet, and there are no points above the trend channel. So what would you guess the correlation coefficient to be here? Definitely negative. Okay. Yeah, so not -1, because remember, if it's -1, then you're going to have all the points fall perfectly in the same straight line. So our colas graph does not look like this. So it's going to kind of be more in here. Still negative, but yeah, so maybe it's -0.8. Again, it's fairly strong because there are no points in that upper triangular region, and there are no points in the lower triangular region. Okay, now, the calculator will calculate this correlation coefficient for you. And so let me show you the steps to that. It turns out that you need only one set of calculator commands to calculate the correlation coefficient and the coefficients of the line of best fit. So your calculator might not be displaying those, so I might have to walk you through how you set up your calculator. But all right, here are the steps. Once you have the data in L1 and L2, go to Stat, and now we want to calculate something. So we're going to move over, and you want to go down to this command right here, which is linear regression, ax+b. So it looks like mx+b, ax+b. That's the one you want. And on your sheet here, Stat, calculate, number 4, enter. And number 4 is the linear regression. So I'm going to select number 4. Now again, I have one of those old calculators where I just need to know what to type in here. But for the new menu calculators, you have to tell it where your X values are, X list, L1. For me, I just type in L1, and then the comma, and then you need to tell it where the Y list is. And we put the Y values in L2, so L2. Now, there's a blank for frequencies. Leave that blank because each one of these data values, these data pairs, appear one at a time. There is no one data value that appears multiple times. And the other thing is the regression equation. And I'll tell you what to do with that here in a second. But you can leave that blank for now. All right, I'm going to hit enter here, and you're going to want to see everything that's on your screen that I see on my screen. Oops, I had an extra comma there. All right, sorry. All right, so there it is. Do you see those 4 numbers?
I don't have the R squared or the R.
Okay. If you've never done this before, your calculator probably doesn't have it either. But here is the R that we're after, negative 0.805, and compare that to what we estimated it to be here. So R equals negative 0.8, I'll call it 806 to round it. All right, some of you don't have these numbers, so I need to take you through a couple of steps so that you turn on the R. It's called a diagnostic, and you want to turn on the diagnostic. All right, so it's not a command that we use frequently, and so commands that we don't use frequently appear in the catalog. So right above the number 0 there is the word catalog. So you'll hit the blue key and then catalog. So it looks like this. And you can see it's alphabetized. So you want to scroll down until you get to the D's. And then there are 2 commands here. One is turn the diagnostic off, and the other one is turn the diagnostic on. And you want to select the turn the diagnostic on. And everybody has to do this one time if you don't see R and R squared. So with the little triangle pointing at diagnostic on, we're going to hit enter. That command, diagnostic on, will go to our home screen. Then we're going to hit enter again, and nothing interesting happens. It just says, okay, done. I've turned the diagnostics on. So now go back to one variable statistics, L1 and L2. And the next time you do it, you should see R and R squared. You'll never have to return to the catalog to do diagnostic on. Once you turn it on, it stays on until you turn it off. So in these problems, in section 4.1 and 4.2, when it asks you to calculate the correlation coefficient, use your calculator. Okay, let's go through now these questions that you see here. Okay, so I didn't talk about this, but they're going to ask you, what is the explanatory variable? The explanatory variable is the x-axis variable. In algebra, I think we called it the independent variable. But in statistics, we call it the explanatory variable. What would explain the weak bones. What would explain the low bone mineral density? What would explain that would be the X, the number of colas someone consumes each week. So X is the explanatory variable. And in this case, it's the weekly colas consumed. The response variable is always going to be the Y. Okay? And for us, it's the bone mineral density, bone strength. Part B, we're going to compute the sample correlation coefficient. In this class, compute doesn't mean compute by hand. It means find the sample correlation coefficient. That's R. And we just found that to be 0.806. Does a linear relationship exist between bone density and colas consumed? So you go to your scatter plot, and is there a relationship? And I think we've already established when the correlation coefficient is as high as 0.8 or negative 0.8, then there definitely is a relationship. Yes, a relationship exists between weekly colas consumed and bone mineral density. Now, usually we're going to use descriptors. And so when you get something like 0.8 or negative 0.8, that is a fairly strong. We also want to indicate whether it's a downwardly sloping trend line or an upwardly sloping trend line. If it's upward, then the correlation coefficient and the slope of the line will be positive. If it's a downward sloping trend, then the R value will be negative, and also the slope of the best fit line will be negative. So we want to indicate that this is an inverse relationship, because as X number of colas consumed increases, the Y, the bone mineral density, decreases. So you'll actually want to say that. As the number of colas consumed each week increases, the BMD, bone mineral density, decreases. So this whole idea of inverse is that as one variable increases, the other one decreases, does the opposite. All right, the next one, it says to find the least squares regression line. All right, this is the one where you want to write down the equation, y equals ax plus b. Now let me show you where you get that. Here was the output. When we were trying to calculate the correlation coefficient, this was the output. In that output, they tell us that A is negative 0.000, and I'm just going to say 3. I'm going to round it to 3 decimal places. And the B value is 0.886, also rounded to 3 decimal places. This is the output of the calculator when we use linear regression.
I have my A and B as the opposite of that.
Yeah, there's that's fine, as long as if you read up here, it probably says A plus BX.
Oh, it does.
Yeah, so as long as, as long as the A is the slope, or as long as the number in front of the X is the negative 0.003, you're okay. You can see there's another option in here. If you go to Stat and Calculate, and I'm unsure why they include 2 of them, but if you scroll down, here's the one I wanted you to select, AX plus B, but there's another one down here, A plus BX.
Oh, okay.
Give you the same output, but they switch the A and the B. So just make sure that if you use the other one, then you're still going to get the same equation that we get, and here it is, y equals negative 0.003x plus 0.886. All right, now, while we have the line, I'm going to graph it along with that scatter plot. So to do that, when you, if you go to the y equals, and you can enter in that equation right here. And so I'm going to enter in the equation, negative 0.003x plus 0.886. So this is the line with those coefficients rounded to 3 decimal places, but usually that's enough precision. There it is. All right, I've got the equal sign highlighted. I've got plot 1 highlighted, and that means the calculator is ready to graph both the scatter plot, plot 1, and it's going to graph the line. So I'm going to hit graph, and there you can see the line of best fit going through right the middle of the trend line, or the trend channel. The line kind of goes right in the middle. So if I were to draw the line of best fit here, it would kind of go something like this, right through the trend channel, something like that. All right, now once we have that line of best fit, then we can make predictions. So the next thing that they ask is, let's see, oh, we have to interpret the slope yet. All right, so the slope is the A, which is the negative 0.003. And the y-intercept, that's the B, that's the 0.886. You'll always be asked to interpret the slope. What is the meaning of the slope? And in order to effectively interpret the slope, you have to use the units and the values of an x and a y. And so the slope is the rise over run, or the change in y over the change in x. So I'm going to write negative 0.003 as a fraction. You can always do this by just putting a 1 underneath the decimal number. The y value corresponds to the bone mineral density, and the x value corresponds to the colas consumed. So when you're interpreting the slope, you want to use the number negative 0.003, but you also want to mention the 2 variables used to calculate the slope. And so the interpretation, we would say something like this: as weekly colas consumed increases by 1 cola per week. So basically, as someone increases their cola consumption by 1 cola per week, the bone mineral density decreases because of the negative by 0.003. So you get the negative from the word decreases, and then you've got the number 0.003. And then you have to provide the correct unit. And for this one, the correct unit is grams per square centimeter. And there's the interpretation of the slope. Next, we have the y-intercept. Generically, the y-intercept is the y value when x equals 0. X equals 0 corresponds to 0 colas consumed. Okay, so we're going to say something like this. We would estimate that for a person who consumes 0 colas per week, that their bone mineral density would be 0.886. All right, so here's the interpretation. A person who consumes 0 colas per week would have a bone mineral density number of 0.886. Again, the unit there is grams per square centimeter. So in part D, they wanted you to estimate or to interpret the slope. And whenever we say interpret here, you'll be expected to write down a couple of sentences, 1 or more sentences in words. All right, and then finally, for part E, this is where we use that equation to make predictions. So we're going to predict the bone density, that's the y value, predict the y for someone who consumes 14 colas per week, about 2 per day. Is this prediction reasonable? All right, so we start with our equation, y equals negative 0.003 x plus 0.886. And then we put in x equals 14 per week. And evaluate by plugging in 14. And get your calculator out and do the arithmetic with these messy numbers. And you get 0.844. And again, the unit is grams per square centimeter. Now, this is probably not reasonable. And the reason for that is that there's lots of things that could determine bone strength. It's more than just the diet, the colas consumed. It's the other things in the diet. If someone who works out regularly, they might have stronger bones than someone who doesn't. And genetics plays a role as well. So there's lots of these variables that would alter somebody's bone mineral density. It's not just cola. But more importantly, when you look at all of these subjects in this study, not a single one had a bone mineral density that was less than about 0.86. So 0.844, our predicted amount here, might not even be a possible bone mineral strength of a human. It might lead to bones that are so brittle that they would just break by walking or something like this. So the other reason is that our data only goes from 0 to about 8 colas. We don't have any data from 8 out to 14. And there's no guarantee that this trend is going to continue. This is called extrapolation, where we try to predict the value outside our data range. And whenever you do that, you have to be careful. And so I would say not a good prediction because the bone mineral density here is too low for a human. All right, we will look at the mathematical formulas next time that show us the relationship between the correlation coefficient and the A and the B in the line of best fit. Turns out it uses means and standard deviations of the individual X's and the individual Y's. But we'll look at that next time.